Greetings. Welcome to the third example for the UAV FSO link. In this particular example, examine the propagation of light from a base station fixed to ground and a UAV receiver that is 500 meters above the ground level with a line of sight 6 kilometer transmission distance, as we have done in the previous two examples. In this particular example, we'll examine two additions to the UAV FSO link. The first is the utilization of multimode inputs. As we have saw previously, having a light connected directly to the component without any multimode input forced the component to generate a Gaussian beam with a 50 millimeter waist. In this particular example, we are using a Lagrange transverse mode generator, and we are generating two modes for each polarization. So there are 4 modes in total. And these are the orders of these Lagrange modes. And if we run the simulation and plot the output of these modes, you can see here that for the X polarization, we have the first mode, and for the we have also a second mode. And we can calculate the mode sum by showing it in the spatial visualizer as such. We can also examine the Y polarization summed modes as well. Now, how to operate this inside our component, we will be running this in a similar way as we've done before. However, for the beam waist calculation, you're selecting the calculated from the incoming modes, as this is a multimode propagation situation. And a lot of the parameters are very similar to what we had before as well. We're also going to be turning on turbulence. We'll do that subsequently, and we'll be examining the effect of beam wander and jitter in this configuration. Now, if you run the simulation without any of those effects included, I will just run it. You'll see that what we'll have is the mode expanding, as we know that the mode will expand as it propagates over the range of 6 kilometers, and the beam waist will increase accordingly. And this is expected. As such, one has to ensure that the numerical window is large enough to capture the complete mode. If we observe here, this is, for example, the initial summed mode in the Y. And if we look at, for example, the Y mode that's summed as well, and you can see that the mode within the same fixed numerical window has expanded significantly as it propagates, and this is expected. In the component, there are actually two particular ways of propagating the mode inside the beam XYZ profile tab. You can see here that a propagation mode. This propagation mode initially by default is independent. It means that the mode will propagate independent from the other modes. And as you can see here that if I look at, for example, the X polarization and I remove the sum, I will actually see here mode 0, and I also have mode number 1. So these two modes are propagated separately. In the other configuration, which is in this here independent, we have combined. It means that the modes are combined coherently. It's a coherent sum at the beginning of propagation and propagates accordingly. So let's run this simulation here and see what that manifests as. And the coherent sum obviously would run faster, as the propagation doesn't need to be calculated for each of the 4 modes, rather than 2 modes where both are added together for X and Y polarizations. So now we can see here that the mode order 1 is empty. If we go down to mode order 0, we have a single coherent mode. That is the sum of all of the input X modes, for example, mode 0 and mode 1, and then propagated down the FSO link. Inside the component, just to note, if you're looking at the sort of expectations of where the beam is going to be, for example, this is the beam is now much wider, and this is calculated because it's a multimode signal, and this is calculated actually as a rough estimate for both X and Y polarizations for all the modes involved. Now, if we simply would like to turn on additional effects involved, we can turn on the turbulence phase mask, and we're using a single phase mask as we have done in the previous examples. And we're also going to be turning on beam wandering and also turning on the UAV jitter, so mechanical jitter as well. And we can examine this running. And in the subsequent representations, we're actually going to try something different as well, as shown in this graph here. I'll explain it here, that in some occasions, the Cn square, which is the index refractive structure, changes with altitude through an altitude model, and it can also change with the path distance. If your line of sight path increases with altitude, then you would expect that this index refractive structure plot versus altitude and versus z propagation distance are going to be very similar. However, there are advanced techniques where one would like to include a spike or increase in the Tn square due to, for example, the propellers involved in the UAV. For example, if the UAV here generates some heat or generates some changes in the index refractive structure, you would like to capture that. So that's going to be our next stage here. So first, let's examine the effect of the beam wandering, beam jitter, and also the effect of the turbulence on our multimode signal. And if we can, in this case, they're all combined. So this is the coherent sum, and we can also examine it for the Y polarizations as well. So, and they also have an effect of the beam wander and the beam jitter and effects on the capture loss and all the other metrics that we've described in the previous examinations. Now, in an effort to so essentially modify the Cn square, if I look here for example, in the component view, you can see now that this is your received plane and this is your received signal, and you can see there's a fair bit of loss here. Let's examine the Cn square as a function of propagation distance, and you can see here this is the Cn square as a function of altitude based on the HVP model. And this is the Cn square as a function of z position. And if I like to have my custom Cn squared, and this is an example of a diagram where the Cn square becomes higher in a specific region, or maybe around 6 kilometers, increases a little bit. So we have some variations that we would like to model for the Cn square. So if you go to the beam wandering, the scintillation tab, and you check the Fright parameter calculation is from the is going to be defined from the Cn squared, and rather than selecting the altitude model, we'll select user-defined Z profile. So now we're going to define our own Cn square versus the propagation distance, and this is the staircase measurements in this particular example, and we could rerun the simulation again, and we're able to actually port those experimental values inside the component. So the purpose here is to really allow the user some additional control to really account for advanced modulation, advanced sort of features, and advanced modeling techniques when it comes to the effects of, let's say, turbulence or the effect of the jet stream area around the location of the drone. So if we examine here, you can see that now we have some other effects, and we observe, for example, here, that this is your index refractive structure versus your Z position. So you can measure in the lab a particular Cn square structure, and you can upload it to your component and try to match what you get experimentally. Thank you very much for your attention.